Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we begin what I think is a very exciting approach to the end of the course. Basically, if everything in life happened at a constant rate, we'd be all through with mathematics right now. Unfortunately, it doesn't. I'm reminded of the story of the transcontinental flight where the stewardess came in and she said to the passengers, one of our engines has quit, but don't worry, the other three engines are strong enough to carry us to our destination. The problem is we're going to be about an hour and a half late. And a few minutes later she came back in and she said, gee, you know, a second engine has quit, but we've still got enough power to get by. We're going to be about 3 hours late. And then she came in a few minutes later and she said, I'm sorry, but the third engine has quit. We still have plenty of power to get us there, but we're going to be about 5 hours late. And one of the passengers looked up and says, my God, if we lose that fourth engine, we're going to be up here all night. And basically, life doesn't work that way. There comes a time when things don't happen at constant rates, and that's what makes the world go around, so to speak. So what I'd like to do today is to introduce to you the topics of non-constant rates. And to do that, we'll start with a few special cases, just so that you get an idea of what it's like. So at any rate, today's lecture is entitled Non-Constant Rates. And what we're going to do is we're going to look at three special types of non-constant rates that come up quite a bit. The first, and perhaps the simplest, is when you have a mixture of constant rates. In other words, you have constant rates, but there's more than one of them in the problem, so the overall effect is that of a non-constant rate. The second one deals with a topic that we haven't talked about yet in this course, and that's measuring the amount of space in a region, which we'll call areas. And the third one, which is probably the most important. In fact, that's an interesting one. Exponential growth is a topic that comes up almost in no matter what field you're in today, whether you're in science, behavioral science, whatever the field happens to be, economics, history, exponential growth is a very, very important topic. So these are the three areas I'd like to look at with you today, and I thought we'd just go through them one at a time, which is probably the only way we can. But let's start with type A first, and that's the mixture of the constant rates. And we've dealt with this before in different contexts. Suppose as a merchant, I go out and I buy 30 coats at $40 each. You see, that's a constant rate problem. Now I go out and I buy 70 more coats, but these coats are $60 each. That's another constant rate problem. So what I've done is I've purchased coats at two different constant rates. And so the question comes up, what did I really spend over here? Well, see, this is a simple problem. We've already dealt with this. 30 coats at $40 each. 30 coats, that's $40 30 times. That's $1,200. And now you spend $60 70 times for the other 70 coats. That's $4,200. So altogether, you've bought 100 coats, and you spent $5,400. In which case, we now proceed as if this were a constant rate problem, and we say the dollars per coat would be $5,400 divided by 100, which is $54, and that's called $54 a coat. And by that, we call that the average cost per coat. See, what it means is if you went out and bought all 100 coats at the constant rate of $54 each, you would have spent $5,400. Notice the danger of an average price over here. See, one price of coat was $40, one price was $60, the average price was $54, which isn't either of the two prices that you paid. Another very form of mixtures of constant rates is when the constant rate only applies to one thing at a time. We almost dealt with that when we talked about in the exercise set of a person going out and writing one check for $24 and one check for $25 and one check for $26. That was really a mixed rate problem. Because what you're saying is you were paying what? $24 per check for one check, $25 per check for another check, $25 per check for a third check. You see, it was a constant rate applied to only one item. And a place where you see this very often is on a road map. In the next four examples that I do, in problems 2, 3, 4, and 5, we're going to use the following road map. It's not all that clear. Just jot this down if you're taking notes along with me. The first segment of a trip is 48 miles. The next segment is 44 miles. The next segment is 46 miles. Then there's a 53-mile segment, a 41-mile segment, and an 8-mile segment. And the first question I'm going to ask you is that if you followed the path from A to B, how far did you go? And notice that this is the same type of problem as saying if you wrote checks for $48, $44, $46, $53, $41, and $8, how much money did you spend? See, basically all we're going to do in getting from A to B is to add up all of these numbers. And I've deliberately written this in the horizontal form to emphasize the fact that I'm expecting you to be using calculators. Obviously, for a problem of this type, it's just as easy to add them up without the calculator. But I think what happens is the vertical form suggests doing it longhand, and the horizontal form suggests using the calculator. You just enter these numbers in the order of their appearance or any way that you want, and it turns out that the length of this trip is 240 miles. We just added up. Now you see, where were the different constant rates here? Each leg of the trip, so to speak, was a different distance. There were 1, 2, 3, 4, 5, 6 legs to the trip. So on the average, each of those segments was 40 miles. See, miles per segment, 240 miles divided by 6 segments. It's as if each of those, in other words, if these spaces between the intervals were all the same, they all would have been 40 miles. But you see, none of the intervals was exactly 40 miles. So, but at any rate, you see, this is a mixture problem of constant rates. And once you do one mixture problem of constant rates, there are a whole bunch of other questions that you could ask. Like over here, this was kind of a silly thing, in a sense, asking 240 miles divided by 6. I mean, who really cares what the average length of each segment was? But there are times when you do care what the average length of something is. Let me give you another example. Let's suppose in making this trip, I have a time constraint. Suppose I have to make this trip in 6 hours. See, and the question then becomes, what must my average speed be in order for me to make this trip in 6 hours? See, speed is what? Miles per hour. Miles divided by hours. So I take the 240 miles per 6 hours. Remember, per means divided by. So I'm going to divide by 6 hours. 240 divided by 6 is 40, and the label would be miles per hour. And what that says is, if I want to make that trip in no more than 6 hours, I'm going to have to average 40 miles per hour. Now, if I average more than 40 miles per hour, I'll make the trip in less than 6 hours. Notice, by the way, how many times in life we say, how fast must I go to make the trip in 6 hours? How often does a person in the real world say something like, I want to get there in exactly 6 hours? Usually you say, I want to get there within 6 hours. See, but the trick is, to find out how to get there within 6 hours, you find out how long it would take you to get there in 6 hours, then anything faster. See how fast you have to go to get there within 6 hours, in exactly 6 hours, and anything faster than that will get you there before the 6 hours. You see, we deal with equalities, but life is really based on inequalities. We don't usually say, I want to make exactly $50,000 a year. We say things like, I want to make at least $50,000 a year. And how do you reach that goal? You figure out what it would take to make $50,000 a year and then just exceed that. So life is inequalities, but we solve them by thinking equalities. At any rate, this gives me a hint. It says if I want to make it within 6 hours, I'm going to have to average at least 40 miles per hour. Well, sometimes as I'm making this trip, I have to think of my expenses. How much gasoline am I going to use? See? And that's going to depend on how many miles I can get per gallon on my car. So problem number 4 says, if you get an average of 15 miles per gallon, how many gallons of gas will you expect to use? And just to remind us of the dimensional analysis, just so that you don't forget that, remember, if you wanted to, you could say what? 240 miles equals blank gallons. Then what you want to do is what? You want to convert from miles, so since they're in the numerator, you put them into the denominator, and you want to bring in gallons. And you're told you can get 15 miles to 1 gallon. So now you see the miles cancel. The label is gallons. And 240 over 15 means 15 goes into 240, and you find out that it's going to take 16 gallons. And by the way, again in the real world, you don't rely on 16 gallons. You say, I'm expecting 16 gallons, but you make sure, if possible, that you account for more than that, because average is a very dangerous thing. You see, you can run into problems, and maybe you won't meet your average. And again, the other thing I want you to see is that rates are relative. You notice the difference over here? In problem number 3 and in problem number 4, we were finding miles per something. But in one case, it was miles per hour, The other case, it was miles per gallon. You see, you can do more than one rate with given information. See all the different things that you can be doing. See all the different constant rates you're finding in this problem. Okay, why did you want to know how much gasoline it was going to use up? If it was a gas rationing situation, you want to know how much of your quota you're going to use up. In most normal real-life situations, you want to know how much gas it's going to cost because gas costs money. And you want to know how much it's going to cost you. So perhaps the next question that would come up would be, oh, before I even get to that, again, I wanted to point out, for those of you who are still frightened of word problems, you can resort to the elementary arithmetic counting way here. 15 miles per gallon means what? On 10 gallons, see, multiply both sides by 10. On 10 gallons, I would go 150 miles. Then, since 150 times 2 is 300, on 20 gallons, I would go 300 miles. So for 240 miles, I'm somewhere between 10 and 20 gallons. And you shouldn't be afraid to use those kind of techniques. Don't be afraid of counting on your fingers or listing things. The most important thing is to get a plausible answer. And if getting the plausible answer means that you have to count on your fingers, do it. And eventually you'll become comfortable enough so you won't have to do it that way. But at any rate, getting back to our sequence of problems, the next problem says at $1.20 per gallon, how much should you expect to spend for gas? Well, you know you're going to need 16 gallons. At $1.20 a gallon, you're going to be spending $1.20 16 times. That's $19.20. And notice that I stopped doing the arithmetic here because I assume that either you can multiply this thing out or you have your calculator and you're just taking 16 times 1.2. Again, if you were doing this by dimensional analysis, you want to convert from gallons to dollars. So you take the 16 gallons and multiply that by dollars per gallon, and you still get the 16 times 1.20. And just one more advertising gimmick. I've never yet seen a gas station that charges $1.20 for gas. I always see them charging $1.99. Again, notice the psychological effect of how this looks like a penny cheaper than this when it's really only a tenth of a cent cheaper. I've never really figured out why gasoline prices are always given like that, but that's sort of irrelevant. Just thought we'd mention these things. And you sort of get the feeling of how this stuff is working out. You see, the easiest way in which to have non-constant rates is to have a whole bunch of different constant rates. Now, the next thing I want to talk about is something that's very important in its own right, and I've just fitted into this module as an application of non-constant rates. But it's the problem of measuring the amount of space in a given region. For example, I've drawn 3 regions fairly much at random here. And what I'm asking is, how much space is enclosed by these regions? Which one encloses the most space, the least? How much more? Do you see that this is kind of difficult? You look at these things, you get an impression, and how do you measure the amount of space? See, there are 2 things that one likes to do in life. One is to get a rough idea of size, and the other is to do things exactly. Like a lot of people, when they have their own recipes, and you say to them, can you give me the recipe? They say things like, well, you use a little flour, you put in about yay much sugar, and when you go to make that recipe, this is not objective enough for you to be able to make the recipe yourself. In other words, if somebody says to you, the water is very warm, is it possible that the water is cold by your standards? You see, in the world of science, what we want is a measuring device that will allow us to measure objectively. Let me give you an example of a simple physical experiment that you can all do. In fact, it's so simple you don't have to do it. You can pretend to do it, and you know what the result is going to be. Imagine that you have 3 containers of water. One has hot water, one has cold water, and the one in the middle has ordinary tap water. You put one hand in the hot water, one hand in the cold water, plunge both hands simultaneously into the tap water, and what happens? The hand that was in the hot water transmits the feeling that the tap water is very cold. And the hand that was in the very cold water transmits the feeling that the tap water is very warm. And the cynic would say, which hand is lying? And the sociologist has a beautiful answer to this. What the sociologist says is, both hands are telling the truth, but they're experiencing a common phenomenon based on a different past history. It's the melting pot idea. Now you see, what happens is, what's hot to one might be cold to another. But suppose you had a thermometer, and you put the thermometer into the tap water. And let's suppose that it registered 58 degrees. See, 58 degrees could be cold to one person, but warm to another person, but 58 degrees is 58 degrees. You see, the thermometer is an objective measurement. Hot and cold are subjective measurements. So to say, well, there's a little bit of space in here is subjective. To say exactly how much, that's objective. And by the way, to handle regions like this, the next lecture, which is a supplement to this one, will deal with that in much more detail. But for the time being, we do in science the same thing an infant does. You know, it's really funny. If you want to see how science and civilization progressed, just watch how a child progresses, and you sort of see a microcosm of the whole thing. You start with the simplest possible problem, and gradually, as you gain experience, you branch out to more difficult things. The easiest region to find the amount of space inside of, and by the way, the amount of space inside is called the area, is a region which we call a rectangle. A rectangle is a four-sided figure, the opposite sides of which have the same direction. That's called parallel. And all of the angles are square corners. That's called a rectangle. See? Right, okay? That's a rectangle. Now suppose I have a rectangle, and suppose it's 3 feet long and 2 feet wide. And I now want to find out how much space is in here. Well, you see, what we do is we, since I'm dealing with feet over here, why not take a unit of area, which is a 1 foot square? See, when you're measuring length, you take a length that's 1 foot. When you want to measure the amount of space inside a region, why not take a little square, each of whose sides is 1 foot? So look what would happen if I do this. You see, with 3 feet, I can form 3 1-foot strips. And with 2 feet, I can form 2 1-foot strips. And if you look at this, dividing this into feet this way and into feet this way, can you see that I wind up with 6 1-foot squares in here? See, the size of each of these 1-foot squares is called a square foot. And how many square feet do I have in here? 1, 2, 3, 4, 5, 6. Well, you see, in this case, it's easy to count. With bigger numbers, it would be a nuisance. I've done a few of these later on in the lesson today, but basically all you have to do here is to multiply the 3 feet by the 2 feet. And I'm going to review this briefly in a minute, but the thing I want you to notice is, remember what we said about multiplication? You multiply the adjectives, but you also multiply the nouns. So 3 times 2 is 6, and feet times feet we call square feet. Just like when you multiply a number by itself, you call it the square of the number. See, feet times feet is square feet. Whenever you hear the noun square feet, you're measuring the amount of space inside. When you hear the word feet, then you're measuring a length. Let me give you 2 problems that people confuse over here. One problem is the distance around. The distance around is called the perimeter. And how far is it to go around this? You're going to go 3 feet, 2 feet, then 3 feet again, then 2 feet again. See, the distance around would be 5 feet. That's called the perimeter. When you hear the noun feet, you know you're measuring around. When you hear the noun square feet, you're measuring the distance inside. See, the perimeter here would be 10 feet. See, 3 feet plus 2 feet is 5 feet. Then you double that, that's 10 feet. The area is 6 square feet. And let me just review that for you. See, the distance around the rectangle is called the perimeter. And to find the perimeter, you add the length and the width and multiply that by 2. Some people say, well, couldn't you take the length twice and the width twice? That's precisely your distributive property. See, I could say what? It's 2 times 3 feet, which is 6 feet, 2 times 2 feet, which is 4 feet, and 6 plus 4 is 10. The amount of space enclosed is 3 feet times 2 feet, and do you see how you get the answer? 3 times 2 is 6. Feet times feet are square feet. And the way we write that is with the exponent 2. Scientists write square feet this way to remind them that in this problem, you're multiplying feet by feet. Well, let's review this by doing a couple of problems that we haven't done yet. And notice again, it's not going to matter, for those of you who are afraid of the metric system and stuff like this, who cares whether you're measuring in feet or in yards or in meters or in centimeters? The principle is going to be the same. I deliberately switched to meters just to show you that nothing dramatic happens here. I say a rectangle is 8 meters long and 7 meters wide. What is its perimeter? And what does perimeter mean? The distance around. And part B says, what is the area? And to help you see this, and as you watch me draw, all of you who happen to be draftsmen, you will realize that as glib as I may be in mathematics, I'm no threat to your job. So we can still be friends here. What I've done is I've tried to draw this rectangle to scale. See, on this particular scale, this represents 8 meters, this represents 7 meters, okay? Now, if all I'm looking for is the perimeter, I just add up the distance around. See, imagine this to be a plot of land. See, one question is, how much fencing do I need to enclose this? Well, I'm going to need 8 meters and 7 meters. That's 15 meters, and I'm going to need that twice. See, so the answer to part A is I add the 8 meters and the 7 meters to give me 15 meters, and I double that to give me 30 meters. In other words, if I were ordering fencing, I would need 30 meters of fencing. Now suppose I'm putting, this is a patio, and suppose I'm painting it, and I know I can get so much paint per square foot. See, the area is how much space is inside here. And how do I find that? You just multiply the length times the width. You see what I'm going to do over here? I have 8 1-meter strips this way, 7 1-meter strips this way. 8 times 7 is 56. Meters times meters would be called square meters. And by the way, I've also taken the liberty of counting the squares for you so that you can see, like when we're doing multiplication of whole numbers, and we showed that 7 times 8 meant to form what? 7 rows, each with 8 tally marks, or 8 rows, each with 7 tally marks. This is exactly the same problem, except that 1-meter squares are replacing the tally marks here. So how do you tackle this problem? To find the perimeter, you add the distances around. To find the area, you multiply the length times the width. And by the way, what becomes exciting here is that just by knowing the perimeter, you don't know how much space is enclosed. Look at this problem over here. It says a rectangle is 10 meters long and 5 meters wide. What is its perimeter and what is its area? At first glance, this might look like a completely different problem from the previous one. I don't know if we can get this in with a long shot or not, but I've drawn the other one to scale also. You see, this is 10 meters by 5 meters, and this is 8 meters by 7 meters. If you look at these two, can you sense that it's not that clear whether they have the same amount of space? But what is interesting is they have the same perimeter. They have the same perimeter. Look, in this one over here, from here to here is 10 meters, from here to here is 5 meters, 10 meters plus 5 meters is 15 meters. I double that, that's 30 meters. So in other words, the distance around this rectangle is the same as the distance around the previous rectangle. In other words, if I had 30 meters worth of fencing, I could form one rectangle that was 8 meters by 7 meters. I could form another rectangle that was 10 meters by 5 meters. In fact, if I had 30 meters of fencing, half of that would be 15. So any length and width that added up to 15 meters would be a rectangle I could form. But look what happens over here. You see, I have 10 1-meter strips this way. See, this rectangle is longer than the previous one. I have 5 1-meter strips this way, so this is narrower. But altogether, what do I have? 10 times 5 is 50, and meters times meters are square meters. So you see, in these two problems, the perimeter is the same, but one rectangle holds 56 square meters, the other one holds only 50, okay? And what's interesting is you may wonder, for a given perimeter, how do I enclose the greatest area? And this is a calculus problem, just to show you how closely related calculus is to what we're doing here. For a given perimeter, the greatest area occurs when the length and the width are equal. In other words, if you're given a certain perimeter and you want to enclose the largest possible area, divide the perimeter into 4 equal parts and form a square. Now, this discussion on area was a means towards an end. What I wanted to get to was discussing squares with you. See, now I say to you, problem number 8 here for today's demonstration, I'm going to ask you to find the area of 3 squares. One is a 1-foot square, one is a 2-foot square, and one is a 3-foot square. And what I want you to do is to find the area of each square. Do you notice that the number of feet is increasing constantly? See, in other words, if you look at parts A, B, and C, isn't the footage the length increasing by 1 at a time. See, 1, 2, 3. That's a constant rate. You're changing by 1 foot per part of the problem. Now, here's a 1 foot square. Okay, a 1 foot square. By a 1 foot square, I mean what? A square, each of whose sides is 1 foot. Here's a 2 foot square. That means each side is 2 feet. What's interesting is this side is twice as long as this side, but how many 1 foot squares fit into a 2 foot square? 4. 1, 2, 3, 4. See, 2 is twice as big as 1, but a 2 foot square is 4 times as big as a 1 foot square. Now let's look at the 3 foot square. See, in a 3 foot square, I can get 3 1 foot strips this way, 3 1 foot strips this way. That's going to give me what? 3 times 3 is 9. Feet times feet is square feet. And I counted these in for you just to have you see this, okay? And in other words, how many 1 foot squares in a 3 foot square? Not 3, but 9. Do you see what's happening here? There's 1 square foot, 4 square feet, and 9 square feet. I'll get back to the shading in about a minute. I just wanted to summarize the results over here. See, the answer to part A is that if the side is 1 foot, the area is 1 square foot. If the side is 2 feet, the area is 4 square feet. If the side is 3 feet, the area is 9 square feet. Do you notice that this relationship is not linear? You see, is not constant? You see, the length of the side is changing constantly at the rate of 1 foot per part of the problem. Look what happens over here. How much did the area change by here? You went from 1 square foot to 4 square feet. That's a change of 3, isn't it? Now in going from 4 square feet to 9 square feet, what do you get? 5 square feet. You see the numbers here? 1, 3, and 5. Here they're all the same, 1, 1, and 1. In fact, you know what the next one would have been? Suppose you had a 4 foot square. What would the area have been? 4 feet times 4 feet would be 16 square feet. And the difference between 9 and 16 is 7. I just wanted you to see that if you start with a 1 foot square, to get to a 2 foot square, you're adding on what? 1, 2, 3 more little squares. And then once you have the 2 foot square, you see what you're doing? Each time you're adding on an L-shaped region. Draw that badly. See, and there's your 5 that you're adding on. See, 1 plus 3 plus 5 is 9. And the next one would have had what? 3 this way, 3 this way, and 1 in the corner. But that's what number theory is all about, and people sometimes show an interest in that. But what I wanted you to see was that when you deal with length, that's constant. When you deal with areas, there's a rate of change which isn't constant. And in fact, let me just go one step further over here. Let me change this problem into another problem that we've already, in other words, let me reword this in a different way. And what I'm going to say is, problem number 9, how many square feet are there in 1 square yard? You see there are 3 feet in 1 yard, so it's very easy to blurt out, oh, I know the answer. It must be 3 square feet in 1 square yard. No, we just saw that a 1 yard square, a yard is 3 feet, isn't it? And we just saw that in a 3 foot square, there are 9 square feet, not 3 square feet. See, the idea goes like this. If you don't want to draw the diagram, you say, look, a square yard means 1 yard by 1 yard. Another name for 1 yard is 3 feet. And 3 feet times 3 feet is 9 square feet. In other words, even though 1 yard is 3 feet, 1 square yard is 9 square feet. And did you notice that from the previous problem? A 3 foot square has 9 square feet in it. The other thing you have to be careful about is with or without a calculator, you can't just memorize a formula. Don't say that the area is the length times the width. You've got to make sure the dimensions are correct. Here's an example. A rug is 4 yards long and 6 feet wide. What is its area? The most common mistake that people make is they say, oh, I'll just multiply the length times the width. And they give the answer as 24, which technically speaking could be right, except that you always have to have a label for the answer. Let's just take a look at this in a little bit more detail. You see, one of the dimensions is 4 yards. The other one is 6 feet. Okay? Do you have the right to just multiply the 2 dimensions? Sure. You can say, okay, the area is 4 yards times 6 feet. But be careful. 4 times 6 is 24, but what are yards times feet? Just like hundreds times thousands are hundred thousands, yards times feet would be called yard feet. Do you ever go into a store and say, give me 24 yard feet? No. You say, give me 24 square feet. You may say, give me 24 square yards. In other words, when you say square yards, you mean yards times yards. When you say square feet, you mean feet times feet. So basically over here, what you want to do is either convert both of these to feet. In other words, you could say what? That 4 yards is 12 feet. Or you might have preferred to convert 6 feet into 2 yards. Either way, you either want feet times feet or yards times yards. You see, in feet, this problem would be 12 feet by 6 feet, which is 72 square feet. And in yards, it would be 4 yards times 2 yards, which is 8. I'm sorry. God bless these erasable. Just as long as I don't wipe my finger on my suit now, would be okay. See, 8 square yards. And notice what happens over here. In going from square feet to square yards. By the way, both of these answers are right. It's just that the adjectives are modifying different nouns. How many 8s are there in 72? Not 3, there are 9. In other words, if you wanted to convert 72 square feet into square yards, see, using the dimensional analysis, this part would still be right. The danger would be, don't say that there are 3 square feet per square yard. There are 3 feet per yard. There are 9 square feet per 1 square yard, and that's where we'd get the answer 8 from. Sometimes we want to do the reverse problem. I thought now I would like to use this chapter as an excuse to motivate the square root key on your calculator. Suppose I tell you that the area of a square is 25 square inches. I like to write it this way to emphasize inches times inches. Now I say, how long is each side? Go for the dimensions first. Since it's square inches, which means inches times inches, it means the side must have been measured in inches. Now you're saying, what number must I multiply by itself? See, the area is the length times the length. What number must I multiply by itself to get 25? And it doesn't take long, especially if you watched our lecture on the calculator where we did the same problem, to discover that the number must be 5. See, in other words, if the area is 25 square inches, the length of each side must be 5 inches. You see, if you start with the length of the side and want to find the area, you square the length of the side. If you start with the area and want to find the length of the side, you do the inverse operation, and that means you take the square root. So if you wanted to do this on your calculator, you would enter 25, press the square root key, unless you have a certain type of calculator where first you would press the square root key and then enter the 25, and then you would read 5 as the answer. The beauty of the calculator is it allows us to make hard problems easier. Suppose I now said to you the area of a square is 50 square meters. To the nearest centimeter, find the length of each side. See, as soon as I hear the word square meters, I know I'm multiplying what? Meters by meters. So I'm saying to myself, what number multiplied by itself gives me 50? See, going over to here, see, I want to get 50 square meters. That means I'm multiplying meters times meters. So I take a guess. I say, what if it was 7 meters? 7 times 7 is 49. Oops, I missed it by just a little. So I'll try 8. 8 times 8 is 64. I missed by quite a bit. You see, 7 is just a teensy-weensy bit too small. That's a word I learned in kindergarten. See, it's a teensy-weensy bit too small, a smidgen too small. 64 is quite a bit too big. So I know the answer is around 7. Now, in most real-life situations, I would stop here and I'd say the answer is around 7. But this problem says I need the answer to the nearest centimeter, which, by the way, if you're dealing with meters, means you want it to 2 decimal place accuracy. It's like if you're measuring in dollars and you want the answer to the nearest cent, that means you need 2 decimal places, the dimes and the cents. Remember, 100th of a meter is called a centimeter. So here's the problem. If I try to keep doing this problem longhand, I get into a real mess over here. So I have to try 7.1, 7.2. If 7.1 is too big and 7.0 is too small, I have to try 7.01, 7.02. It's a real mess. But you see, the calculator doesn't distinguish between 50 being here and 25 being here. See, hard versus, see, this is not conceptually hard. It's computationally cumbersome. See, but the calculator doesn't mind cumbersome stuff. That's the good news of the calculator. It does the cumbersome stuff. See, I enter the 50, I press the square root sign, and immediately what lights up on my calculator is 7 point, and look how many decimal places it gets for me, 071067812. I have to supply the label myself. It's meters, and that's how long each side is. But the problem said to me, round it off to the nearest centimeter. That means to the nearest hundredth, so I go over to here. This is a 1, so I just drop the rest. And so to the nearest centimeter, the length of each side is 7.07. And what's interesting is you can check this out. If the length of the side were actually 7.07, that times itself should give you the 50. When I multiply this out, what do I get? 49.9849. That's still too small, but isn't that a lot closer than when I took 7 times 7? Now, when I try 7.8, that should be too big, but not as big as 8 times 8 was. You see, what happens over here, I'm still going to be surrounding the 50. 7.08 times 7.08 is 50.1264. You see, when I just dealt with whole numbers, I trapped the 50 between 49 and 51. What I've done here is I've trapped the 50 between 49.9849 and what? 50.1264. And by the way, if I needed even more accuracy, the calculator has done that for me. See, this problem told me to round off to the nearest hundredth, but how many digits did I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. I could have rounded off to 6 places or to 7 decimal places. And by the way, just to check the final step here, you see, if I use the 7.07, the size of my error, subtracting that from 50, is 0.0151. If I use the 50.1264, subtract 50 from that, the size of my error is 0.1264. So what that shows me is that 50 is between these two numbers, but since this is smaller than this, it means I'm closer to this one, and that verifies longhand that to the nearest hundredth, to the nearest centimeter, the length of each side of that square is 7.07 meters. Okay? You sort of have the idea on that. We're going to do a lot more of that type in the textbook and the study guide, and also there is a supplementary lecture on areas. In fact, that's the next lecture in the course before we do the problem-solving set. But there is the third type I wanted to show you, and that's exponential growth. And exponential growth is when the rate of growth feeds off of what's already grown. See, it's like, again, when we're talking about the cost of living index, and you say the cost of living went up 1/2 of 1%. That means 1/2 of 1% on top of what's already happened the previous months. It doesn't mean from the first day you started measuring. See, and let me give you an example of that. The easiest example and the least militant, I guess, is compound interest. And we can apply this to population growth. We can apply it to bacteria growth. We can apply it to a lot of things. But for the time being, let's just look at compound interest. That's where you earn earnings on your earnings. Suppose, for example, that a bank says that they will pay you 7% interest compounded annually. Compounded annually means that you will get that 7% interest for that year. But the next year, the 7% is going to be added on to what you've already earned. Let me just give you an example this way. See, first of all, let's make sure for those of you who still get nervous about percents that you know what 7% means in terms of money. 7% means 7 per 100. So for every $100, you're going to earn $7. And suppose a person says, yeah, but I'm not going to put 100 in the bank. Well, multiply both sides of this by 10. Remember, we can always multiply a rate problem by the same number on both sides. See, 7% doesn't just mean $7 for every 100. It also means what? $70 for every 1,000. You see, if I multiply by 10 here and multiply by 10 here, I don't change the rate. And also, if I multiply by 10 again on both sides, I can also say it's what? 700 per 10,000. And if you had 20,000 in here, that would be what? Twice 10,000 is 20,000, so twice 700 is 1,400. So on $20,000, you would earn $1,400 at 7% interest. So here's where compound interest comes in. I say you invest $10,000 at an interest rate of 7% compounded annually. How much money do you have, A, after 1 year, B, after 2 years? A is a very easy problem. We just did it. We just said over here that if you have $10,000 in the bank at 7% interest, you're going to make $700. So what does that mean? It means at the end of 1 year, you have your original $10,000 plus another $700. that's $10,700. Excuse me. Another way of visualizing the answer here is, at 7% interest, every dollar is now worth $1.07. When it comes to banking, it doesn't make any difference whether you have one deposit of 10,000 or 1,000 deposits of $1 each. In other words, notice that in this particular problem, you can view the $10,000 as being $1 10,000 times. Each dollar becomes worth $1.07, so you have what? $1.07 10,000 times. And if you multiplied 1.07 by 10,000, you get the same 10,700 that you got over here. Okay, that was the easy part. Now, part B said, how much do you have after 2 years? Here's the tricky part. You see, at simple interest, if you got $700 interest 1 year, you're going to get $700 interest the next year. But on compound interest, you no longer have $10,000 in the bank. What you have in the bank now is $10,700. So now you make what? $1.07 on each of the $10,700. You see what I'm saying? So you don't have $10,000 anymore. You have $10,700. So now you're making $1.07. In other words, $1.07, 10,700 times. By the way, just to make this easier to handle, since it's the money that you have in there that you're more interested in, let me put the dollar sign on this one and leave it off on this one. In other words, my 10,700 gets multiplied by 1.07. And by the way, to help you see what the pattern is here, what was the 10,700? Wasn't that what I got after I multiplied 10,000 by 1.07? You see, what I'm really doing here is at the end of the second year, see, after the first year, I had multiplied by 1.07. The second year, I multiplied by 1.07 again. You see what the pattern is going to be? Every year it's in there, I multiply the new amount by 1.07, and so I keep multiplying by 1.07, 1.07, etc. But getting back to the main thrust over here, at the end of 2 years, you have $11,449 in the bank, which compares with, if you had been getting simple interest, you'd have made $700 twice, which is $1,400, so you would have had $11,400, which isn't bad, but you've still got $49 more this way, and this will continue to open up for you. See, the next problem simply says, how much will you have after 3 years? Well, after 2 years, you had $11,700. Each of those dollars is going to earn you $1.07, so you're going to multiply what? $1.07 by 11,700, or written this way, you see what's happened? You see, you multiplied the first year by 1.07, then you multiplied by 1.07 again to see what you had at the end of 2 years, then you multiplied by 1.07 again to see what you have at the end of the 3 years. So if I want to use exponential notation, see, how do you abbreviate 1.07 times 1.07 times 1.07? You just write it 1.07 to the third power. Remember, 10 to the third power meant 10 times 10 times 10. 1.07 to the third power means 1.07 times 1.07 times 1.07. But at any rate, how could you do this on your calculator? You just start with the 10,000, you multiply by 1.07, then multiply by 1.07 again, then multiply by 1.07 again. That kitty story keeps coming up, and the answer comes out to be $12,198. Versus, if this had been simple interest, you'd have made $700 for each of the 3 years. That would give you $2,100 in interest. That would give you $12,100, which is what? $98 less than what you made this way. And we can go on and on and on. For example, suppose I said, how much money will you have at the end of 10 years? Well, see, the concept stays the same. The computation becomes more complicated. See, at the end of 10 years, see, every year I have to multiply the 10,000 by 1 point. Every year I multiply by another 1.07. So in 10 years, I've multiplied by 1.07 10 times. Even with the calculator, that gets tedious, doesn't it? I have to multiply by 1.07, 1.07, 1.07, 1.07, 1.07. That's only 5 of them. I got to do that 5 more times. If you've got a calculator that has what's called a y to the x key on it, it's a beautiful investment if you're going to be dealing with compound interest problems. Because all you do with that kind of a calculator is you start off by entering what's going to be raised to the power. You enter the 1.07. Then you press the y to the x key. Then you press the exponent, the 10. Then you press the equal sign, and all of a sudden you read 1.967151357. That's my calculator. And by the way, what that says is, if you left $1 in the bank at 7% interest compounded annually, at the end of 10 years, that dollar would be worth 1.967, etc., okay, dollars, which rounded off to the nearest cent would be $1.97. Now, in going from $1 to $1.97, isn't that roughly double? Just for the sake of the last part of our discussion for today, let's assume that at 7% interest compounded annually, you double your investment every 10 years. Look what that says. See, so at 7% compounded annually, your investment essentially, see, it's a little bit off, doubles every 10 years. So suppose it was 7 point something percent, so it exactly doubled in 10 years. Look what happens. Now it's called 0 years. That's a nice motivation for negative numbers, in fact. You see, if I call today 0 years, what was last year? It was 1 below 0, 1 before 0. But we won't get into that. That's algebra. But for the sake of argument, see, right now, which we call 0 years, you have $10,000. 10 years later, that's doubled, hasn't it? So you have $20,000. Now, here's where the compound interest comes in. After 10 years, you no longer have 10,000, you have 20,000. So what doubles the next 10 years is the 20,000. That becomes 40,000. The next 10 years, it's the 40,000 that's doubling. That becomes 80,000. The next 10 years, you see, it's the 80,000 that's doubling. That becomes 160,000. And the next 10 years, it becomes 320,000. So if you put $10,000 away now, after 50 years, if you don't touch it and the interest rate stays the same, that's $320,000. You see, it's doubling every time. In fact, this becomes a very insidious thing when it comes to retiring. See, let's suppose you started this at age 20. At age 60, see, 40 years later, you've got $160,000. You say, yippee, I'll pull it out of the bank. But now you look and you say, gee, if I leave it in there for 10 more years, the whole $160,000 is going to double, so you're really losing out on what? Another $160,000 by taking it out. And basically, this type of exponential growth tends to make people get very greedy. You know, the stakes go up very, very phenomenally. By the way, germ cultures work the same way. If bacteria double every 10 minutes, you see what this says? Replace years by minutes and call this bacteria count. If you had 10,000 bacteria and they're doubling every 10 minutes, after 50 minutes, you have 320,000 bacteria. Same with population growth. Try to trace your ancestry. No matter what your lifestyle is, you had 2 parents. And each of your parents had 2 parents. And each of their parents had 2 parents. If you go back 20 links this way, 2 to the 20th power is already bigger than 1 million. In other words, you have over, if you go back to 20 generations, you have over 1 million ancestors, assuming that there's been, not ancestors, ancestors, assuming there's been no intermarriage. But let me show you what this really means in terms of graphing. Remember we said that constant rates graph as a straight line? Look what happens over here. I haven't taught you graphing, but I think this is easy to read. On the horizontal line here, I have graphed the number of years in gaps of 10. In other words, each of these lengths represents 10 years. And each of these little lengths over here represents $10,000. So look what happens. You see, every 10 years, this height is doubling. See, you had this much. What does it do in 10 years? It doubles. Therefore, the length of this line is twice the length of this line. Now what happens during the next 10 years? This is the amount that doubled. So this length here is going to be double this length. You see, it's not increasing at a constant rate. You see, in going from here to here, this went from 10,000 to 20,000. That was an increase of 10,000. But in going from here to here, this didn't increase by 10,000. It increased by 20,000. You see, this is 10,000. This is 20,000. This is 40,000. What happens during the next 10 years? This goes up to 80,000. And you see what's going to happen over here. Each of these lengths is double the previous length. And so if you now try to visualize this in a graph, this is going to be a very steeply rising graph. And that's what we mean by exponential growth. You see, let me just end today's lesson with a very quick summary. See, when you graph something, linear means it's a straight line. See, constant means a straight line. If you have several constant rates in the same problem, it just graphs as several straight lines. In general, things will graph in different shapes. And what advanced math is all about is analyzing these different shapes. And one of the most important of these shapes is the shape that represents exponential growth. Whenever the rate of change is proportional in a ratio to whatever's present, you get exponential growth. And that comes up in calculus, it comes up in finance, it comes up in bacteria counts, it comes up in almost everything. At any rate, I think this gives you enough of an introduction about non-constant rates. There will be an enrichment lecture before the next exercise set to discuss areas with you in more detail. In particular, I'm going to talk about a circle, which is a very famous non-straight line. And until that time, have fun, study hard, and stay young.